Hi, folks. I got a couple of questions on, well, both this question itself and questions like it. So I thought I would take a minute and kind of give some advice or perspective on answering this type of question. So we have a study that was trying to compare the difference between students admitted through special programs. Of course, the details of the setup aren't necessarily all that important, but it's good to give us some context. And medical students who are admitted through the regular admission process. It was found that the graduation rate was 0.929 for the medical students admitted through special programs. So that's the probability of success for our system for medical students admitted through the special programs. If 12 of the students from the special programs are randomly selected, find the probability that at least 11 of them graduated. So we're selecting 12 people. So that's our N is 12. There are 12 trials, and we're trying to see how many successes and failures we have. Now I'm going to make not really a chart here, but more just a diagram of our possible outcomes. So I'm going to look at our 12 individuals. Oops, I forgot 9. So 8, 9, 10, 11, 12. So these are the possible things that could happen. Of these 12 randomly selected individuals, none of them may have graduated. 1, 2, 3, 4, 5, 6, 7 graduated, 8 graduated, 9, 10, 11, or all 12. So we could find the probability of any of these individual results coming up with our general binomial tool. So for example, if we wanted to know what is the probability, say, that 9 graduated. Now that would be that exactly 9 graduated, no more or no less. So we could use our binomial tool not only in Excel, but in our calculator, that binomial tool with the PDF. That PDF gives us individual probabilities. So the binomial PDF with the 9 would give us the probability of exactly 9 happening. We don't often use that individual probability tool though, because often we don't want to know what's the probability of exactly 9 happening. We usually care about these at most, at least, or in between problems. So when we have these 12 students, if we want to find the probability that at least 11 of them graduated, I'm going to actually recommend you guys make a diagram like this, or at least if it's a lot more numbers than just 12, like just a number line with some tick marks on it, so you can represent what your values are. So if we want to find the probability that at least 11 graduated, well, if only 2 graduate, that's not at least 11. 3 isn't at least 11, 4, 5, 6, 7. The only things that are at least 11 are 11 and 12. So we need those 2. Now we could take the PDF for 11 and the PDF for 12 and add those together if we wanted to. And that would be fine. It's only 2 of them. But if it had asked, say, at least 7, that would be 1, 2, 3, 4, 5, 6 to add up. I don't want to do that. So whenever you see this at least is always going to be some value and everything above it. And above is not what our tools mainly do. Our tools mainly give us cumulative values below. So if we want to know this, at least this value for 11 and up, generally what we're going to do is find what's below it and subtract from 1. If we use our binomial CDF tool, remember that CDF is cumulative, it adds up everything that happened before. That binomial CDF with an x equals 10, notice 10, not the 11, that binomial CDF 10 will give us everything from 0 up to and including 10. And then our at least will be 1 minus that binomial CDF at 10. I'm, of course, abbreviating this function, but so if we want at least, that means we want 11 and 12. Our tool doesn't handle 11 and 12 nicely, but it does handle from 10 down nicely. So use it to find from 10 down. And remember that since all our probabilities have to add up to 1, subtracting it from 1 is very nice, very handy. So some of you have mentioned, you can handle the at most, but handling the at least is hard. This would be at most 10. If you can find at most 10, subtract from 1 will get you at least 11. If we wanted to say find the probability between, say 6 and 10, if we wanted to find the probability that between 6 and 10 will graduate, well, again, our tool doesn't do between very well. It does from a place and down. But again, this binomial CDF is the blue, the whole blue section there is the binomial CDF. If we want the pink section, well, we can take the blue section and just subtract out the 5, 4, 3, 2, 1, 0. So we could get the between 6 and 10 by taking the binomial at 10. That'll give us 10 and down. Subtract the ones we don't want, the binomial from 5 and down, and that's going to give us between 10 and 6 without having to take 6, 7, 8, 9, and 10 separately and add them together. So by using our subtractions, either subtracting from one or subtracting from each other, we can use that one tool that only wants to measure downward and manipulate it to giving us what we want when we want things above, when we want things in between, or sometimes we want everything below, and that's fine, that's great. So if we wanted to find that probability of at least 11 graduating, that 1 minus our binomial distribution tool, cumulative, CDF at 10 will do that. Let's see, if 12 students from the special program are randomly selected, find the probability that exactly 9 of them, that's what I was saying before. That's the binomial PDF at 9. If you're using Excel, then it's the binom.dis, and it would be 9 of 12 with a probability of 0.929. How to force it do the difference between a PDF and a CDF is this last logic statement. As you learned on your lab, if this last logic statement is false, you're doing a PDF. If it's true, you're doing a CDF. And I think Svetlana on her example typed false and true, but you can actually just put in a 0 for false and a 1 for true. So 1 minus the binomial distribution, this would be 10 of 12 with a probability of 0.9291. That 1 is going to make it a CDF instead of a PDF. So either on the calculator or on the Excel, using that CDF versus PDF gives us individual values versus that value and everything that came before. Would it be unusual for a randomly selected 12 students in the special program to get exactly 9 that graduated? Well, if we found this percentage, if that percentage is small enough, usually less than 0.025 or less than 0.05, depending on the threshold that you're using, and your book talks about which threshold it wants, then either yes or no of it being unusual. Down here, if 12 of the students randomly selected find the probability that at most 9 of them graduated. So at most is running out of colors up here. Go to the purple. At most 9 is 9 or less. So 9 or less. Well, that's what our cumulative tool wants to do. It wants to do that or less. So our binomial CDF with 9 will automatically give us that 9 and everything below it. It is weird that 9 or less is at most 9, but both 9 or less means 9 is the highest value. Saying at most 9 tells you the highest value possible is 9. So they're both expressing that top bound. So that binomial CDF 9 will give us the probability, and I would guess this would be quite small as well. Should be bigger than the exactly 9, but I think it's still going to be small. So whether it passes that threshold or not depends on what that value is. So hopefully this gave some perspective on ways to approach this. I really do recommend writing out this kind of chart for them, even if it's like you don't want to write out all of them. If you just go, 0 through 12, if you want, say, somebody asks you for at least 10, well, that means you're going to need from 10 upward. Well, that means you'll need the CDF less than 9, and then 1 minus the CDF at 9 will give you that part above. So even just having a little diagram with some tick marks on it can be really helpful for approaching these problems with a little bit more solidity. Hopefully that helps. I'll send this out to everybody. If it does help, great, let me know. If it doesn't help, and you can come up with a more specific question in here, then great. I'll send something out and see if I can help.